Hi, I'm Bob. Let's do computer exercises 10 to 12 today for Chapter 8. For computer exercise 10, I report the usual standard errors in parentheses and the heteroskedasticity robust standard errors in brackets. The difference between them is negligible. In Part 2, for the linear probability model, the variance of y is the product of the probability of success and failure, px times 1 minus px. The variance of the error term equals the variance of y because we treat the explanatory variables and the parameters fixed. Then we use the formula of the variance. The expected value of the squared error term equals the variance of the error term because the expected value of the error term is 0. So we have equation 1. The squared residuals, mu hat squares, are the estimates of the expected value of the squared error term, and the fit value y hat is the estimate of the probability of success. The squared fit value is the estimate of the squared probability of success. Therefore, when we regress the squared residuals on the fit value and its squared term, we should have alpha 1 approaches 1, alpha 2 approaches minus 1, and alpha 0 approaches 0. We verify it in Part 3. We find that coefficient estimates correspond to the theoretical values described in Part 2. The coefficient on y hat is 1.0097, close to 1, and the coefficient on squared y hat is minus 0.9703, close to minus 1, and the coefficient on the intercept is close to 0. In Part 4, we verify that the fit values are all between 0 and 1. We generate the h hat equals to the fit values times 1 minus the fit values. Then we create the weight equal to the inverse of it. Finally, we run the linear probability model by weighted least squares. I report the weighted least squares estimates with the usual standard errors. They do not differ in important ways from the OLS estimates. The estimates are similar and the significance is basically the same. The Stata commands for computer exercise 10 are as follows. Let's find answers to exercise 11. We use the keep command to keep the observations for one-person families. For Part 1, we add the interaction term between income and the dummy variable of eligibility of the 401k plan. We use double hashtags in Stata to construct the interaction term. The option VCE specifies the robust standard errors. The usual standard error for the interaction term is 0.124. The t-statistic is 2.78 and its p-value is 0.006. The heteroskedasticity robust standard error is 0.220, larger than the usual standard error. The t-statistic is 1.56 and its p-value is 0.119. The interaction effect is statistically significant at the 1% level using the usual standard error, but insignificant at even the 10% level using the robust standard error. For part 2, we generate the weights equal to 1 over income. Then we estimate the model by weighted least squares. We put the weights inside the bracket in Stata. The usual standard error for the interaction term is 0.130. The t-statistic is 2.27 and its p-value is 0.023. The robust standard error for the interaction term is 0.160. The t-statistic is 1.84 and its p-value is 0.066. We find that the interaction effect is statistically significant at the 5% level using the usual standard error in the weighted least squares model. And it is still significant at the 10% level using the robust standard error. For part 3, the coefficient on E401K is the estimate when income is 0. It is not of much interest by itself. The sample average income is $29.45 thousand. If we plug it into the model, the coefficient on E401K at this point will be about $6.5 thousand. In the last part, we construct a new interaction term and estimate model by weighted least squares. The coefficient on E401K becomes 6.68, which is statistically significant at the 1% level. For people with $30,000 of income, the difference in the total financial assets between those eligible for the 401K plan and those not is around $6,680 on average. Here are the Stata commands for computer exercise 11. Let's do exercise 12. We estimate the model by OLS. I report the usual OLS standard errors in parentheses and the heteroskedasticity robust standard errors in brackets. The robust standard errors are larger than the usual standard errors. It results in smaller t-statistics in absolute values and less significance using robust standard errors. For example, the expenditure effect on math test performance is statistically significant at the 10% level using the usual standard error, but insignificant using the robust standard error. The 95% confidence intervals are wider with robust standard errors. For Part 2, we obtain the OLS model's residuals and fit values. Then we generate the squared residuals and the squared fit values. To do the special case of the y-test, we regress the squared residuals on the fit values and the squared fit values. The F statistic for the overall significance is large, 132.7. It is strong evidence against the long hypothesis of homoskedasticity. In Part 3, we follow the procedure of feasible GLS to correct for heteroskedasticity. We obtain the G hat as the fit values from the regression of log squared mu hat on mass 4 hat and squared mass 4 hat. Then we generate the H hat by exponentiating the G hat. The weights will be 1 over H hat. We estimate the model by weighted least squares using the weights. The estimated equation is as follows. There are noticeable changes in the coefficient estimates. The coefficient on log expenditure increases from 3.5 to 6.5, and the effect becomes more statistically significant. The negative enrollment effect cuts half. For Part 4, the heteroskedasticity robust standard errors allow misspecification of the variance function. The weighted least squares estimates with robust standard errors are as follows. The robust weighted least squares standard errors do not differ much from the usual weighted least squares standard errors. The largest change will be the standard error for the log enrollment. The larger robust standard error leads to a p-value of 0.012, while it is 0.002 with the usual standard error. For the last part, for estimating the effect of spending on mass 4, the weighted least squares measure is more precise than the ordinary least squares measure. The usual and robust standard errors are smaller by WLS than by OLS. The effect is statistically significant at the 5% level by weighted least squares, but not by ordinary least squares. Here are the Stata commands for computer exercise 12. Thank you for solving the computer exercises with me. I hope it helps. See you soon. Thank you for watching this video and subscribing to my YouTube channel. See you next time.